Hello everyone, and welcome back to Math 220A Mathematical Logic. Lecture 15, Real Closed Fields. In today's lecture, we concentrate on the field of real numbers. R plus times 0, 1. And our task is to understand the theory of this field. Unlike the theory of algebraically closed fields, the theory of the field of real numbers does not have quantifier elimination in the language of rings. Indeed, we can show that any quantifier-free formula in the language of rings, phi of x with a single free variable x, defines either a finite or a cofinite subset of the field To see this, we just remark that every such quantifier-free formula in the language of rings, phi of x, is a Boolean combination of polynomial equalities and inequalities. So Boolean combination of formulas of the form p of x is equal to 0 for some polynomial p in a single variable x with integer coefficients. This we already saw during the discussion of the theory of algebraically closed fields in an earlier lecture. But then, of course, any such polynomial, as long as it is non-zero, has only finitely many solutions in any field. And so any Boolean combination of such sets is going to be either finite or cofinite. But if we consider the formula phi of x given by exists z such that z square is equal to x, then in the field of reals, phi defines the set of non-negative real numbers which of course is in particular infinite and co-infinite. Set. So we see that then it cannot be defined by quantifier-free formula. So this example shows that the theory of the field of reals does not eliminate quantifiers. However, we will see that all that is needed to be added to the language in order to obtain quantifier elimination is the ordering. So here we have the set of positive real numbers, and we will see that with the ordering, the theory does eliminate quantifiers. This is a celebrated theorem of Tarski and Seidenberg. Towards a proof of this theorem, we need to review some results from the theory of ordered fields. So algebraic background on ordered fields all of the results that we will use are due to Artin and Schreier. First definition: a field F is said to be orderable if there is a linear ordering on the field such that F together with this ordering is an ordered field where a pair of F with an ordering is called an ordered field if the ordering is compatible with the field operations, i.e. for all x, y, z in F, we have that x is less than y implies x plus z is less than y plus z, and x is less than y and z is greater than 0 implies that x times z is less than y times z. So both addition and multiplication respect the ordering. In this case, we say that F with this ordering is an ordered field, and the field is orderable if there exists a choice of a linear ordering on its underlying set, which is compatible with the field operations. Remark: although there are unique orderings of the fields R and Q, which are compatible with the field operations, in general, an orderable field might have many different orderings. For example, consider the field Qx of rational functions in one variable has 2 to the aleph naught distinct orderings exercise. Now, there exists a purely algebraic characterization of the orderable fields, not referring to the existence of the ordering explicitly in any form. For this, we have the following definition. A field F is called formally real if -1 in this field is not a sum of squares, i.e. There are no a1 through an in the field F such that -1 is equal to the sum of the squares of the ai's, I from 1 to n, for any n and for any choice of the elements ai in F. Of course, in any ordered field, all squares are non-negative. Thus, every orderable field is formally real. And the following theorem, due to Artin-Schreier, shows that the converse is also true. So if F is a formally real field, then F is orderable. Indeed, if A is an element of F and minus A is not a sum of squares of elements of F, then there exists an ordering of F in which A is a positive element, so greater than 0. Because the field of complex numbers is the only proper algebraic extension of the real field, the real numbers have no proper, formally real algebraic extensions. Fields with this property will play a key role in the proof of Tarski-Seidenberg, so we formalize it in the following definition. A field F is real closed if it is formally real with no proper formally real algebraic extensions. From this definition, it is not clear that being real closed is in fact an axiomatizable property. The following theorem, again due to Artin-Schreier, allows us to axiomatize real closed fields. Theorem: let F be a formally real field then the following are equivalent. 1. F is real closed. 2. The field extension of F by adding the element I is algebraically closed. Where I is the square root of -1. And 3, for any element A in F, either A or minus A is a square, and every polynomial of odd degree has a root. So note that the second condition is obviously satisfied in the field of by the field of real numbers, since its extension by the square root of -1, the field of complex numbers, is algebraically closed by the fundamental theorem of algebra. And we see that this is equivalent to the other two properties. Now, the equivalent condition 3 is the one that we can explicitly axiomatize using first-order sentences. So, corollary: the class of real closed fields is axiomatizable as structures in the language of rings proof. We can axiomatize real closed fields by the following: 1. Axioms for fields. And we use to denote the sentence given by the conjunction of these finitely many axioms as phi field. 2. For each natural number n greater or equal than 1, the axiom for all x1 through xn, x1 square plus x2 square, etc., plus xn squared plus 1 is not equal to 0. 3. For all x there exists y such that y square is equal to x, or y square plus x is equal to 0. And 4. For each n, a natural number, the axiom for all x0 through for all x2n, there exists y such that y to the power 2n plus 1, so odd power, plus sum over I from 0 to 2n, xi times y to the power I is equal to 0. So now in these axioms, one expresses that we have a field, 2 expresses that the field is formally real, and the axioms schemas 3 and 4 express that the condition 3, the equivalent condition 3 in the theorem for characterization of real closed fields is satisfied. So even though this shows that the class of real closed fields is axiomatizable as structures in the language of rings, we already saw that we cannot expect to get quantifier elimination result in this language. So instead, we will study real closed fields in the language of ordered rings, which consists of the language of rings together with the ordering binary relation symbol. So now, if f is a real closed field, and we have that 0 is not equal to a, an element of f, then exactly 1 of a and minus a is a square. So we already saw this result. So this allows to order the field f by the following definition. So we say that x is less than y. We define it to hold if y minus x is a non-zero square in the field. Then we can check that this is indeed an ordering of the field compatible with the field operation, and it is the only possible ordering of f. And then we define the theory RCF. So let this be the theory in the language of ordered rings, axiomatized by the axioms given above for real closed fields. And the axioms for ordered fields. Expressing that the ordering is compatible with the field operations. So the models of the theory RCF are exactly the real closed fields with the canonical ordering. And also note that the ordering is definable by the formula in the language of rings exists Z such that z is non-zero and x plus z square is equal to y, then it follows by our discussion of definitional expansions of theories that if F is a real closed field and some subset of some power of the base set is definable by a formula in the language of ordered rings, then X is already definable by a formula in the language of rings. The following theorem of Artin-Schreier provides an alternative axiomatization for RCF. We have that an ordered field F is real closed if and only if whenever P of X is a polynomial in a single variable over F, A, B are two elements of the field such that A is less than B in the ordering, and P of A times P of B is less than 0. So this means that the signs of the values of the polynomial on A and B are different. Then there is C, an element of the field, such that A is less than C is less than B, and P of C is equal to 0. So of course, in the case of the field of reals, this simply follows from the intermediate value theorem due to the continuity of polynomial maps. If it takes two values of different signs on some point C in between A and B, it has to take 0. But we also see that this is in fact equivalent to the property of being real closed for an ordered field. So this condition can be easily axiomatized by first order sentences as well. Next, by the definition with algebraic closure discussed in the earlier lectures, we define the corresponding real closure of a formally real field. So if F is a formally real field, then a real closure of F is a real closed algebraic extension of F. So real closed field containing F and algebraic over it. By Zorn's lemma, one can show that every formally real field F has a maximal real algebraic extension then this maximal formally real algebraic extension is in particular a real closure of F. So real closures always exist. Now they may not be unique. For example, let F be the field of rational functions. We can take F0 to be F with an adjoint square root of X, and F1 to be F with an adjoint root of minus X. Then, by the earlier theorem, providing several equivalents of being formally real, we have that both F0 and F1 are formally real, let Ri be a real closure of Fi, then we claim that there is no isomorphism between R0 and R1 fixing F, because we have that X is a square in R0, but not in R1. So this shows that unlike the situation for algebraic closures of a given field, we don't have the uniqueness up to isomorphism fixing the field F. So some further work needs to be done to show that any ordered field has a real closure, where the canonical order extends the ordering on the original field F. Towards this we have the following lemma. If F less than is an ordered field, X is a positive element in F, and X is not a square in F, then one can extend the ordering of F to an ordering of F with the square root of X adjoined to it. Proof: we can extend the ordering on F to the ordering on F with the square root of X adjoined by defining that 0 is less than a plus b square root of X, so every element is of this form, if and only if we have 1, b is equal to 0, or and a is greater than 0, or 2, b is greater than 0 and a is greater than 0, or x is greater than a square over b square, or 3, b is less than 0 and a is less than 0 and x is less than a square over b square. So now one can easily verify that this is indeed an ordering on the field F with the square root of X adjoined to it. We have the following corollary of this lemma. 1. If F with an ordering is an ordered field, then there is a real closure R of F such that the canonical ordering of R extends the ordering on F. This is 1. And 2, the substructures of models of RCF are precisely the ordered integral domains. Proof: 1. Successively applying the lemma, we can find an ordered field, say L less than, extending the ordered field F less than, such that every positive element of f has a square root in L. Now we can apply Zorn's lemma to find a maximal, formally real, algebraic extension R of L, and as we have that every positive element of f is a square in R, then the canonical ordering of R extends the ordering of f and of course R is a real closure. So this is one. Now two, of course clearly any substructure of a real closed field is an ordered integral domain. So conversely, if D less than is an ordered integral domain, and if we let f be the fraction field, of D, then we can order f by saying that a over b is greater than 0 if and only if both a and b are greater than 0, or both a and b are less than 0. So this gives an ordering of the field f. Now by 1 we can find some real closed field R with an ordering such that f with an ordering is a substructure of R with an ordering. So this gives us 2. Now, even though we have already observed that for a formally real field may have non-isomorphic real closures, if we consider it with a given ordering as an ordered field, then there will be unique real closure which is compatible with the ordering of f. So more precisely, if f less than is an ordered field and R1, R2 are real closures of f where the canonical ordering extends the ordering on f in both R1 and R2, then there exists a unique field isomorphism phi from R1 to R2 such that it fixes the original field f pointwise. So phi restricted to f is the identity map on f. Note that because the ordering of a real closed field is definable in the language of rings, this isomorphism phi also preserves the ordering. We often say that any ordered field f less than has unique real closure, but what we mean by this usually is that there is a unique real closure that extends the given ordering. We now have all the algebraic background about real closed fields needed to prove the main theorem, the quantifier elimination result. So we have theorem Tarski-Seidenberg, the theory RCF of real closed fields admits quantifier elimination. And of course, recall we are working in the language of ordered rings. Proof. Once again, we're going to use the semantic criterion for quantifier elimination that we have discussed earlier. So suppose that we're given F, a common substructure of K and L, two models of RCF, and assume we are given phi of V W bar, a quantifier-free formula in the language of ordered rings, and let A bar be a tuple from the common substructure F and be an element of K such that K satisfies phi of B A bar, and we want to find some B prime in L such that now L also satisfies the formula phi of B prime A bar. Claim 1. We may assume that F is equal to L. So in particular, F is itself a real closed field. This is very similar to our argument in the case of algebraically closed fields. So since we have that F is a substructure of K, in particular we have that F is an ordered integral domain, we let R with an ordering be the real closure of the fraction field of F compatible with the ordering on F. Now let K prime be the set of all alpha in K such that alpha is algebraic over the fraction field of F. So this gives us a subset of the field K. Now it follows from K being a real closed field that K prime is also a real closed field. For example, using our characterization of those fields which are real closed among those which are formally real, namely that for any element of the field, either the element to its additive inverse is a square, and every polynomial of odd degree has a root. So in this case, we can find, of course, such elements in K, but as long as polynomial is with coefficients from F, we have that in particular, it's going to belong to K prime as well. So this way we see that K prime is also a real closed field. And since it's algebraic over the fraction field of F, it also gives us a real closure of this fraction field. Similarly, we can construct L prime, the real closure of F in L, respecting the ordering on F. Then, by the previous theorem, the uniqueness of real closures, we know that there exists an isomorphism f from k prime to L prime, which fixes f pointwise. But now note that if the formula phi of x a bar, which we know has a solution in k, if we could also find a solution in k prime, then applying this isomorphism, which fixes the parameter tuple a bar pointwise, so the image of such a solution in k prime would give us a solution in L prime. So L prime would satisfy the formula phi of f of b a bar, and hence it would hold in L as well. So this shows that it's enough to prove the theorem, assuming that f is equal to k prime. So the situation where we have a real closed field, which is a substructure of another real closed field. So this demonstrates the claim. So next, we note that for any polynomial p, we have that p of x is not equal to 0 holds if and only if p of x is greater than 0 or p minus p of x is greater than 0, where we allow x to be a tuple of variables. And we also have that p of x bar is not greater than 0 if and only if p of x bar is equal to 0 or minus p of x bar is greater than 0. Hence, with this in mind, we may assume that the formula phi is a disjunction of conjunctions of formulas of the form p of v w bar is equal to 0 or p of v w bar is greater than 0. So of course by the disjunctive normal form we assume it's a disjunction of conjunctions of the atomic formulas and the negations, and now because of these two equivalents we can assume that they're all only of these two kinds: polynomial equalities to 0 or polynomial inequalities greater than 0. As in the case of algebraically closed fields, once again, if the disjunction is satisfied by B, then there must be at least one disjunct which is satisfied. So it would be enough to show that phi of V a bar is of the form conjunction over all I from 1 to n, pi of V equals to 0, and conjunction over all I from 1 to some natural number m, qi of V is greater than 0 for some polynomials p1 through pn and q1 through qm, all polynomials with coefficients in f in a single variable x. So we're assuming that this formula has a solution in K, and we want to find a realization for this formula in F. Now, if any of the polynomials pi of x is non-zero, then B, since it realizes the corresponding polynomial equation, is algebraic over f And since f, by assumption, is real closed, so has no proper formally real algebraic extensions, in this case we must have B is an F, hence we are done. So we may assume that the formula phi of V a bar is in fact of the form conjunction QIV is greater than 0 for I from 1 to m. So we arrived at a situation very similar to the situation of algebraically closed fields, but instead of an non-equality, we have an inequality. Yeah? So instead of saying that Qi is not equal to 0, now we have a specific sign, so Qi is greater than 0. Now recall our characterization, fact characterizing real closedness from earlier. So a field is real closed if and only if when we have that the polynomial p takes different signs for some a less than b in a real closed field, then there is some c between a and b such that p of c is equal to 0. So this implies that for each I, the polynomial qi in our list can only change signs at zeros of qi, and all zeros of qi are in f, because f is real closed by our assumption. So it follows that we can find some ci di in f such that ci is less than b is less than di, and qi of x is greater than 0 for all x in this interval ci di. Then we let c be the maximum of the ci's, and we let d be the minimum of the di's, so cn dm. Then, since b is in each of these intervals, we have that c is less than d. Remember, the ordering on f and on k agree, so k extends the ordering on f. So we have c is less than d, and the conjunction overall I from 1 to m, qi of x greater than 0, holds for all c less than x less than d. But then it follows that we can find some b prime in f such that f satisfies phi of b prime a bar. Since, of course, the ordering of the field f has to be dense, so we can always find a point in between any 2 points, C and D. So this concludes the proof of the quantifier elimination result. As an immediate corollary of the quantifier elimination, we obtain that the theory RCF is complete. Proof. So we already know that the theory has quantifier elimination. Now, every real closed field has characteristic 0. So contains the rational numbers real closed field F, let's say. Therefore, R-alg, the field of real algebraic numbers, i.e. the real closure of the rational numbers is a subfield of any real closed field thus for any real closed field F we have that R-alg is an elementary substructure of R, and so we have that R-alg is elementarily equivalent to R. In particular, elementarily equivalent to the field of real numbers. So this shows that the theory of the complete theory of the field of real numbers is given by the axioms for real closed fields. We can also remark that since the theory RCF is complete and the axiomatization that we gave is clearly recursive, the theory RCF is decidable. This is an important meta-mathematical result, in particular because all of elementary geometry, so asking various questions about the existence of lines parallel to a given line, intersecting a given point, or something about intersections of circles, spheres, etc. So all of these problems can be stated in the first order way in terms of certain sentences about the real numbers using the coordinatization. So this result can be viewed as decidability of the elementary geometry, and was viewed one of the last successes of Hilbert's program on decidability of various areas of mathematics before Gödel's incompleteness results. Thank you very much for your attention.